still good. All right, so we go down the path. So now we got this integral. Hopefully you guys got a feel for conceptually what we're trying to do. So now we got this gnarly integral to solve. We do a substitution of w is equal to r squared, or so dw is 2r dr. I'm just moving stuff around. This dw over 2r, and sort of r dr is r dw over 2r. So those guys cancel each other. So then I'm going to plug all this stuff back in to my integral. So I get a, so e. By the way, this little squiggly thing means e perpendicular to. So this means that the only component electric field we're calculating here is perpendicular to the sheet. Why are we deciding to do that? Because by inspection, we said all the non-perpendicular components are going to cancel each other out. Okay, I didn't prove that to you guys, but I just said, look, you guys can clearly see, right? So that guy gets you a. Always beware of people who tell you can clearly see something. 0 to infinity, and I'm plugging everything in. Okay, so I'm end up with this mess. And then what was my next step? So now what did I do? I cleverly got rid of the r. Remember, it was r dr up here. So it's a integral of the form r dr with this r squared in the bottom. So okay, with the substitution, I got rid of that. Now I'm stuck with this. And now you desperately look into Google, into all the tables of integrals, look for something like this form, and you see this, which is, I had to go look it up in a general form. There is a solution for integral of bx plus c to the n dx. Okay, so what does that look like? Well, in this case, b would be 1, right? X is the same as w, c is the same as a squared, and n is to the minus 3/2. You guys with me? So I found this in a table of integrals, and the solution to it is equal to 1 over b to the n plus 1, bx plus c to the n plus 1. I just looked this up. Okay, no, didn't do any magic. So again, in this particular case, b is equal to 1, n is equal to minus 3/2. So the solution is minus 2 over x plus c to the 1/2. No, sorry. W, thank you. W, c is what, sorry?
A squared.
C is a squared. Okay, so let me plug all that in. I'm going to end up with, so with all these goodies and the limits, I end up with minus a sigma over 2 epsilon naught. Not skip any steps, sorry guys. A sigma over 4 epsilon naught minus 2 over 1 plus w plus a squared to the 1/2 from 0 to infinity. So I end up with 2 minus a sigma 2 epsilon naught. 1 over infinity to the 1/2 minus 1 over a. This is really, sorry. This is infinity plus a squared to the half. Because that was the limit of the integral, right? You guys with me? So this guy is basically looks like 1 over infinity. This guy looks like 1 over infinity. Like infinity is a lot bigger than a squared. The reason it's w, I plugged in infinity for w. Infinity plus a squared is infinity. 1 over infinity is 0. So this guy's 0. So upshot is we end up with sigma over 2 epsilon naught. That's our solution. Who else is weirded out by this? Are you weirded out by this? Huh?
Yeah, 80 is taken out entirely.
Yes. So now you have no dependence on distance away from the sheet. So you have constant electric field, like no matter what the distance is away from this infinite sheet of charge, your electric field is the same. So I have no, besides a mathematical geometrical explanation, like so our infinite sheet, you know, if you were, it was sitting in front of you, or if you were in Alpha Centauri, you would experience the same electric field away from this sheet. Very, very unexpected. I have no explanation for you. So I guess the point here being is you have to do, like, it's fine to have a feel for a point charge, but you know, you start having to do the actual math to figure out what the electric field looks like once you get into even really simple geometries away from that, okay? I mean, we had like an unexpected effect from the infinite line, but you know, being 1 over distance versus 1 over distance squared, this is even weirder because there's no distance involved at all. This electric field goes on and on forever.
Which that makes conceptual sense because if you thought about it as a line, both horizontally and vertically, the distance wouldn't matter because you're going infinite. So if you thought about your line on a horizontal span, the distance, the way you explained it is when you get closer it's because of the vector calculus.
Yeah.
But now that was in one dimension. So the vector calculus works out in both directions.
Yeah.
So which is why, conceptually, no matter where you are, you're infinite in both dimensions.
Yeah, yeah. I think that's what, like, it kind of makes sense from there. But if you told me without us doing any of this stuff, I just said infinite sheet, stop me in the hallway and say, if I had an infinite sheet, what would happen if you're like 1,000,000 miles away? I would have some kind of a distance explanation for you, I am sure. Right? But like, when we walk back from the fact, we see like why it may not be the case. But anyway, the point of this thing being that it is like somewhat unexpected. Okay, so I'm going to describe example 3, but of course we won't have time to do it, but I'm going to describe it to you guys. Okay, example 3 is, you guessed it, guys, I gave you the punchline. 1D, 2D, 3D. So if you had a sphere, does this look like do you guys remember this from quiz 0? Quiz 0, okay, so if you had a sphere and there was a uniform charge distribution in the sphere, right? So you had a rho coulombs per meter cubed. So you had uniform charge distribution in the sphere somehow. So somehow you crammed all these charges uniformly in the sphere. They wouldn't like it, they'd be repelled by each other, but somehow you kept them in there, right, uniformly distributed. What would be our solution here? Well, what you would sort of do if you have a taste for masochism, right? You would now, so remember we did the effect of a of a little line segment, the effect of a area segment, which was in the form of a ring. Well, now we got a effect of a little volume segment over here. Okay, on some charge over here. Okay, so we can figure that, we can divide the thing into that. But then I would have to put a little volume segment here and find the effect on that. No volume, just remember this is a sphere, it's not like a, it's a solid sphere. Okay, so I gotta take these infinitesimal segments all the way on the inside and different angles as they're spread around. So, no go, right? This is gonna be a nightmare of a integral to try to do with the same techniques that we used for the linear and the 2D, okay? So, fortunately, there is a better, much simpler approach, and that's called Gauss's law. And again, we won't actually get to it here, but basically it kind of gives you a feel, as you'll see, it's a much simpler way to try to figure out what the effect of electric field is in a complex pattern. So to some extent, the examples we gave was to show you guys that, yeah, you do need to do the calculations to figure out what it is. That's the first thing. Second thing is, like, things start getting complex, okay, as you move from linear to 2D, 3D. So this is the reason we're gonna go look at Gauss's law. Again, Gauss's law just comes from Coulomb's law. So I'm not gonna add anything to Coulomb's law. There's no new discovery of anything. So it's a way of using Coulomb's law is the way I look at it. Okay, guys. Just a question, sorry, is this like, am I droning on? It's kind of like, I'm actually pretty happy to be here in class with you and getting some good interaction, but is it too slow, too fast? Make sense? Confusing? Everybody with me? Okay. Okay, guys, thanks.